It rose from the inner light like a fugitive ember, small, dim, unremarkable at first glance, yet carrying within its silence a secret that would ripple through the careful order of celestial understanding. As 3i Atlas retreated from the sun, climbing the long arc that leads outward into the cold dominions beyond Mars, something impossible began to occur. Instead of fading, instead of surrendering its brilliance to the deepening dark as every comet and icy wanderer must, it grew brighter. A shard from another star, forged in the distant architecture of an alien system, was behaving as if it were waking up, and astronomers trained to expect obedience from the universe's well-tested patterns found themselves staring at a light curve that felt like a whispered rebellion. The mystery did not announce itself with fanfare. It arrived quietly, riding on narrow beams of reflected sunlight gathered by telescopes across the world. A small icy nucleus, likely no more than a few hundred meters across, should have passed by. The sun shrugged off some vapor, ignited a brief plume of dust, then faded into obscurity as it withdrew. This was the script nature had written billions of times. Comets brighten as they fall inward, then dim as they drift away. Their lives unfold with the same inevitability as tides, but 3i Atlas betrayed that rhythm. The deeper it climbed into the cooling light, the more fiercely it shone. Its coma grew, its tail thickened, and its brightness surged in a way that seemed almost inverted from everything known. The sun's heat should have been loosening its grip. Instead, it appeared to be stirring it. The standard expectation that solar proximity dictates activity began to unravel. Something inside this interstellar visitor refused to abide by thermal logic. The enigma was sharpened by its heritage. This was not a native child of our solar system. It came from the dark beyond, carrying the memory of another star's creation, another protoplanetary disk's chemistry, another era and environment entirely. It drifted for millions of years through interstellar night untouched, unheated, undisturbed. The sun should have been only a brief encounter in its long journey, a momentary warmth, a brush with light, not an awakening. Yet the data suggested something more dramatic. For a body so small, its sudden brightening after perihelion was astonishing. Its luminosity rose in a curve that bent sharply, as if some inner reservoir had ruptured, as if some dormant substance had been triggered not by the sun's heat at closest approach, but by the shock of leaving it. Observers watched as the photometric readings ticked upward night after night. They studied the figures, recalibrated instruments, cross-checked with other teams. The numbers held. 3i Atlas was defying its script. To those who study comets, brightness is a language. It conveys information about dust-gas surface activity and internal transitions. But this brightness, the kind that grows, while distance increases, spoke in a dialect rarely heard. Such oddities have appeared in the past, but all within the family of solar-born comets' bodies, whose past composition and behaviour were at least partially understood. This object was different because it carried no ancestral context. It offered no established expectations, and so each unexpected shift felt amplified, each deviation heavier with meaning. As scientists examined the evolving images, they saw an object shedding material at a rate inconsistent with retreating heat. The coma expanded not as a dying ember, but as an intensifying flame. Even when the sun's influence waned, the activity mounted as though 3i Atlas contained layers that were reacting not to heat itself, but to the rate at which heat disappeared. Something within was destabilized by cooling and inversion of the ordinary sequence of thermal events in icy bodies. The cosmos does not often reveal its mysteries through paradox. It usually speaks in gradients, in gentle transitions. But here the paradox stood plainly, a comet brightening where it should dim, intensifying where it should relax, evolving, as if governed by physics from another cradle of stars. In this anomaly, observers felt the presence of something profound. Not necessarily catastrophic or revolutionary, but instructive, as though a small shard drifting between worlds carried the overdue reminder that not all cosmic rules are universal. Some are local truths born of our own solar system's history, its chemistry, its long conversations between sun and planets. But beyond our boundaries, the universe composes itself differently. And now, in the faint glow of a retreating interstellar wanderer, the difference was being illuminated with startling clarity. As the nights passed, the brightness curve sharpened. Astronomers accustomed to predictable cometary behavior found themselves revising models, adjusting assumptions, testing hypotheses, that stretched the understanding of sublimation, thermal inertia, and structural instability. The mystery grew not in dramatic leaps, but in quiet increments, each additional photon a clue, each data point a whisper of something concealed. In the public imagination, interstellar visitors are often seen as exotic emissaries, but in the scientific realm they are precious for their rarity. 3I Atlas was only the third confirmed interstellar object. It carried the weight of expectation, the hope of sampling the geology and chemistry of another star's nursery without ever leaving home. But instead of quietly offering its secrets, it chose to complicate them. Its refusal to dim its refusal to decline into obscurity pushed astronomers to ask questions that felt both intimate and vast. Why did it brighten now? What slumbering materials were shaken awake? What structural fractures were unfolding? What volatile compounds hidden in its core were expanding, boiling or transforming as the sun's heat faded? And why did these reactions not trigger earlier at the moment of greatest solar intensity, but only afterward once the heat began to fall away? There was poetry in the paradox, but also unease. If an object from beyond the sun behaves in ways fundamentally different from comets born here, what other assumptions were fragile? What hidden architectures exist in interstellar chemistry? What forgotten pathways of planetary formation might lead to materials that ignite not with warmth, but with cooling, not with approach, but with departure? Each night the brightness rose a little more. In that rising arc the mystery gathered power. It became less a curiosity and more a quiet challenge, a question suspended in the dark between stars. And as 3I Atlas drifted outward, slow and serene, its unexpected glow illuminated not merely the dust surrounding it, but the deeper boundary between what is known and what is only beginning to be imagined. When the first faint streak of light appeared in the data stream from the Asteroid-Terrestrial Impact Last Alert System, Atlas, few suspected it would become the third interstellar object ever identified, and even fewer imagined the enigma it would bring. Atlas, perched atop the volcanic slopes of Mauna Loa and Haleakala, existed for vigilance. Not discovery, its mandate was to scan the heavens for dangerous near-Earth bodies. Yet on that quiet night beneath the cold stillness of Hawaii's high-altitude darkness, its automated survey swept across a patch of sky and recorded a whisper of motion. A moving point, a traveller cutting softly through the background of fixed stars. The system flagged it. The algorithms trained to detect slight shifts applied their mechanical patience, reading the faint brightening, tracking, the displacement mapping its trajectory. But at first the detection was not extraordinary. A new comet, perhaps another inbound visitor from the Oort cloud, was a familiar story. These icy wanderers arrived often enough, though each carried its own peculiarities. The early measurements suggested a modest body faint and distant, its coma not yet developed. Initial orbital solutions placed it on a path that seemed nearly parabolic, a common illusion for long-period comets just beginning to reveal themselves. Nothing yet hinted at the truth. In the days that followed, other observatories joined the effort. This was the ritual of the astronomical community sightings, verified positions, refined, orbital parameters sharpened. As telescopes across the globe gathered more data, Chile, Spain, South Africa, Australia. The orbit began to take shape, and soon a whisper crossed the communication channels among comet observers: the eccentricity was creeping above 1.0. Not slightly, not through numerical accident, but decisively. The curve of its path no longer belonged to a bound object. It had no home in the sun's domain. It was interstellar. The designation came swiftly. 3 Atlas. The third confirmed interstellar object after Oumuamua and 2I Borisov. And this one, unlike its predecessors, still lingered in a favourable geometry for observation. It approached perihelion with anticipation, not as a fading trail like Oumuamua had been, nor as a fragmenting storm like Borisov, but as a fresh subject whose story could be watched unfold in nearly real time. The discovery rippled with excitement. Astronomers remembered how Oumuamua had slipped through unnoticed until it was already receding, its secrets largely sealed. They remembered how Borisov had begun to break apart, its comet-like nature, clear, but its deeper chemistry only partially charted. Now with 3I Atlas they had time to collect spectra time, to watch its outgassing time, to compare it with the comets born in the solar system. The promise lay not just in observation but in contrast. Each interstellar visitor was an ambassador from a different cradle of stars. Early predictions were simple. As it approached the Sun, it would brighten, according to models honed across decades of comet studies. Dust release gas jets heating gradients. These processes followed patterns. It would flare before perihelion, then dim afterwards. That was the standard script. Yet beneath those early expectations, subtler threads of curiosity unfolded. Some wondered whether its composition might differ radically given its alien origin. Others speculated whether unusual volatiles might evaporate at different temperatures, producing deviations in its behavior. But even these speculations were gently framed within the assumption that the overall light curve would still obey the typical rise and fall trajectory. In the days surrounding perihelion, telescopes captured 3I Atlas with increasing clarity. Its coma appeared stable. Its dust behavior aligned with expectations. Spectral signatures suggested typical volatiles, water, perhaps carbon monoxide, faint traces of organics. Nothing yet hinted at the paradox that would soon emerge. The scientific community observed with cautious optimism. This was the part of comet observation that felt almost ritualistic, watching the visitor approach, tracing its gradual unveiling under solar heat. Everything unfolded according to plan. It brightened as expected, then passed its closest point to the Sun with no extraordinary deviation. And then, as it drifted outward, something subtle began to whisper through the numbers. The decline was slower than it should have been. At first the anomaly was nearly invisible, so small it was lost in the noise of observational error. But as nights accumulated, the quiet discrepancy grew more pronounced. The brightness plateaued, then began to rise again, ever so slightly yet undeniably. Instruments calibrated precisely confirmed the trend. Observers cross-checked against atmospheric conditions, detector responses, calibration stars. Still the brightening persisted. Teams compared notes. Conversations in scientific forums carried a tone of puzzled restraint. No one wanted to declare something unprecedented based on early signs. Comet light curves have misled researchers before dust bursts, delayed outgassing waves, rotational modulations can all complicate predictions. But gradually a consensus started forming. The brightening was real. The question shifted from "is this happening" to "why is it happening?" Some recalled the earliest days of monitoring when 3I Atlas had seemed so compliant with ordinary behavior. They wondered if its interstellar origin might mask delayed thermal reactions in deeper layers. Others considered whether the surface crust had cracked only after perihelion, exposing fresh material. A few proposed that mass shedding, not sunlight, was driving the brightening, but none of these explanations fully fit the timing, and all relied on processes common to ordinary comets, which felt insufficient for a body that had spent millions of years in interstellar cold, its chemistry, perhaps unlike anything forged in the Sun's domain. This was when the discovery began to shift from curiosity to puzzle, and still, its story remained anchored in those first nights: the detection by Atlas, the confirmation of an unbound trajectory, the global cooperation that followed. These were the foundational steps, the moments when humanity first glimpsed the interstellar shard and began unwinding its path. Before the anomaly, before the paradox, before the rising brightness curve defied expectation, there was the simple act of noticing a telescope, catching a faint motion against the stars, and recognizing a visitor from beyond. It is in these early days that the mystery's emotional weight resides. For discovery is not merely mechanical, it is the beginning of an encounter. The cosmos unfolds itself not in grand gestures, but in quiet ones, one detection, one pixel, one arc of motion. From that first moment, 3I Atlas began weaving its narrative into human curiosity. And as its presence strengthened, as the orbital calculation solidified, as its trajectory revealed its alien provenance, astronomers felt the familiar shift from routine observation to deep inquiry. Because in astronomy, every discovery is both answer and question. Every new object is a reminder that the universe is older, stranger, and more inventive than the equations we write to describe it. The discovery of 3I Atlas followed this pattern, but with a gravity unique to interstellar visitors. The object was not just another comet, it was a relic of a world we would never see, shaped by a star whose light would never reach Earth with naked eyes. And the first steps of identifying it were steps toward unraveling a history that did not belong to our solar system. Later, the brightening would complicate everything. It would draw scientists into an escalating investigation into spectra and dust models and theories of exotic ices. But at the beginning, before the anomaly emerged, there was only the serene simplicity of discovery. A faint point, a moving object, an orbit unbound, a visitor from another star. And it was within this quiet emergence that the seeds of the coming shock were planted long before anyone suspected just how profoundly that brightness would refuse to fade. The first hints of trouble arrived not with alarm but with quiet disbelief, as though the universe had slipped a contradiction into the data and waited to see how long it would take for human eyes to notice. Astronomers studying the emerging light curve of 3I Atlas had expected a gentle downturn after its passage around the Sun, a decrease in brightness consistent with every known rule governing cometary behaviour. Yet the numbers refused to bend in that direction. They rose instead, subtle at first, then unmistakable. Along the precise instrument-calibrated line where the light should have been falling away, an upward kink appeared. Within days, that kink grew into a slope, and that slope sharpened into something approaching defiance. There was no dramatic flare, no explosive event captured in a single image. Instead, the mystery unfolded through persistence. Night after night, as telescopes tracked the object across a widening arc of sky, its brightness continued to climb. Researchers checked atmospheric conditions, exposure times instrumental, drift calibration stars, every conceivable source of error. Nothing reconciled the anomaly. 3I Atlas was brightening after perihelion. It was behaving as if sunshine were no longer the governing force of its activity. Scientific shock does not always come from spectacular catastrophes. Often it emerges quietly through the stubborn refusal of reality to match the elegance of theory. This was one of those moments. For more than a century, cometary physics had been grounded in the simple relationship between heat and activity. Approaching the Sun warms the nucleus. Warming triggers sublimation. Sublimation drives dust release. Dust releases light. Retreat reverses the chain. Even the strange comets, those fragmented, chemically odd or dynamically unstable, respect the underlying gradient of solar heating. Yet here was an object that inverted the gradient. A body from beyond the solar system was responding to the Sun not as a warm furnace, but almost as a catalyst whose influence peaked long after the direct heat had passed. The implications were unsettling. If the brightening were a minor deviation, a slow decline mistaken for a rise, astronomers could have classified it as a measurement artifact or a delayed dust burst. But the shape of the curve rejected such mundane explanations. The increase was too long, too smooth, too persistent, and it coincided with the object's growing distance from the Sun, as though some deeper internal process triggered by heating, but not completed until cooling was now unfolding. For many memories of Oumuamua stirred its strange acceleration the way it drifted off course without visible jets. That first interstellar object had already challenged expectations. Now the third was doing something equally confounding. Two anomalies do not make a pattern, but they do erode complacency. The solar system seemed to be telling astronomers that objects forged under other stars obeyed rules that earthbound scientists had not yet encountered. The emotional shock grew from the idea that something as fundamental as thermal behaviour, a cornerstone of cometary science, might not hold universally. Processes assumed to be foundational could in fact be local peculiarities of our own system's formation environment. The universe has never promised consistency. Still, humanity relies on patterns, and the breaking of a pattern as basic as post-perihelion dimming carried with it an almost existential disquiet. Then came the realization that this brightening was not merely anomalous, it was dramatic. Observers began calculating the rate of increase, comparing it with known comet outbursts. The numbers placed 3I Atlas among the most unusually active small bodies ever recorded, and unlike a typical outburst which fades quickly, this rise endured. It suggested not a surface event but a structural or compositional transformation, something deeper and more volatile than the familiar ices of water carbon dioxide or carbon monoxide. If the brightening were the result of exotic ices materials that sublimate at temperatures far below those dominant in the solar system, then these compounds had survived eons in interstellar cold, only to awaken after the Sun's warmth had begun to recede. This defied intuition. Super-volatile ices such as nitrogen or oxygen-based compounds should be triggered near perihelion, not after it. Yet the timing implied that the heating phase merely primed the nucleus, and that the true transformation began only as cooling set in. A more troubling possibility involved structural instability. If the Sun's heat had introduced microfractures into the nucleus, then internal collapse could proceed on its own timetable independent of distance. Cooling could contract layers unequally, driving further fragmentation. Such internal processes might release dust long after the surface had passed maximum heating. But this explanation too struggled with the scale of brightening. The amount of dust implied an energy release far greater than simple cracking. At conferences and in private correspondence, scientists debated the emerging puzzle. The brightening challenged not only thermal models, but also assumptions about material strength, grain size distribution, and the thermal inertia of interstellar matter. Some worried that their models were not merely incomplete, but fundamentally provincial, constructed around comets born in this one solar system. Perhaps interstellar space forged bodies from substances unfamiliar to local experience. The shock deepened when teams compared 3I Atlas with 2I Borisov. Borisov had behaved like a classic comet despite its alien origin. It fragmented and outgassed in ways consistent with known solar system processes. So why did 3I differ so drastically? Were they born in fundamentally different conditions? Was 3I older, colder, more deeply altered by cosmic rays? Or was its chemistry so unusual that it represented a category of object humanity had never encountered before? Even the simplest questions grew unsettling. Why did it wait until after perihelion to erupt into greater brightness? What stored energy was now being released? What chemical architecture allowed such delayed behavior? And beneath these scientific questions lay quieter, more philosophical ones. If objects wandering between stars carry with them unfamiliar physics, what else might be roaming the void? How many assumptions about the universe rest upon local experiences mistaken for universal truths? The shock surrounding 3I Atlas was not that it brightened, it was that the brightening contradicted a foundational narrative. As its luminosity grew while it slipped back toward darkness, astronomers were left with an unnerving sense that the object was not merely unusual but revelatory. It was a reminder that the cosmos is larger than human models, and that the universe's most profound surprises often arrive not with explosions, but with quiet incremental deviations along the edges of expectation. The brightening curve continued its steady ascent, and with it the mystery deepened. The greatest shock had been recognized. 3I Atlas was not following the rules, it was writing its own. As the steady rise in brightness sharpened into a clear and measurable trend, astronomers turned their attention toward the accumulating data photometry spectroscopy and high-resolution imaging, hoping that within these quiet streams of numbers, the true nature of 3I Atlas might begin to reveal itself. The mystery no longer lived in rumour or isolated observations. It lived in spreadsheets, in the spectral fingerprints of faint gases, in the shimmering halos of dust seen through Earth's atmosphere and even faintly from space-based instruments. What emerged from these efforts was not clarity, but a deeper strangeness. The more closely 3I Atlas was measured, the less it resembled any familiar comet. The first hints came from its coma, the glowing envelope of gas and dust drifting around the nucleus. Measurements of its expansion rate suggested that dust was being released not only steadily, but with increasing intensity after perihelion. This contradicted the expectation that a comet's activity wanes as it recedes from the Sun, and its surface cools. Instead of shrinking, the coma grew denser and more extended, as though some internal process had begun to accelerate rather than subside. The velocities of dust grains inferred from the thickness and shape of the coma suggested a surge in sublimation-driven pressure. Yet the timing made no sense. It was as if the nucleus had grown more active while being denied the very heat that typically triggers such behavior. Spectroscopic observations added further complexity. When scientists dispersed its faint light into constituent wavelengths, they expected to find signatures of the usual volatiles: water vapor, carbon monoxide, carbon dioxide, and perhaps traces of more exotic compounds. And indeed, some familiar lines appeared. But there were anomalies lurking in the patterns. The ratios of certain emissions diverged from solar system norms. Water signals were present, but weaker than expected. Carbon monoxide appeared stronger, hinting that deeper layers were being exposed, or that 3I Atlas had retained an unusually high concentration of supervolatiles from its interstellar past. Some instruments reported spectral hints of organic compounds, though faint and difficult to confirm. These signatures carried the possibility, still speculative, that the object's chemistry had been shaped by high-energy cosmic ray bombardment during its long journey between stars, creating layers of complex molecules that differed from those found in typical comets. If true, This would mean that the brightening reflected not simply physical changes, but chemical ones, responses occurring only as certain thresholds of heating and cooling were crossed. Telescopic images told their own story. High-definition captures from observatories in Chile and the Canary Islands revealed subtle, morphological changes, faint jets beginning to bloom, tail shifting orientation, and structures forming within the coma that suggested active and uneven release of material. These jets were not symmetric. They did not align neatly along solar radiation or rotational axes. Instead, they hinted at localized vents opening irregularly, perhaps, due to internal stresses triggered by rapid temperature changes. In some frames, astronomers perceived what looked like faint streaks or diffuse fragments, though none were definitive enough to confirm a breakage event. Still, the imagery raised the possibility that 3I Atlas might be shedding material in pulses, or microfractures too subtle to produce obvious fragmentation, yet significant enough to influence its brightness. Radar, though limited by the object's faintness and distance, offered no contradiction. If anything, its silence contributed to the mystery. No strong echoes, no indications of large coherent surfaces, no hints of a metallic or solid core. The radar returns, what little there were, painted a picture of a porous, fragile object typical of comets, but inconsistent with the level of sustained activity now observed. Data from space-based instruments added another layer. Though 3I Atlas was not an ideal target for major missions, some spacecraft capable of surveying faint objects captured its spectral behavior beyond Earth's atmospheric interference. These clean spectra deepened the puzzle. They revealed that the object's gas production rates continued to rise even as solar flux dwindled. The timing curve of these emissions shifted upward in a pattern more reminiscent of delayed thermal waves propagating through layered ice than of direct sunlight-driven sublimation. This suggested the possibility that sunlight had penetrated deeper into the nucleus than expected during perihelion warming subsurface ices that required time to conduct enough heat to transition into vapor. In such a model, the peak of activity would lag behind the peak of heating, much like how the hottest time of day on Earth occurs after noon. But this analogy was imperfect. The magnitude of the brightening went far beyond what simple thermal inertia could explain. Something else was amplifying the response, some feedback mechanism or chemical phase transition that turned delayed heating into rapid release. One hypothesis involved amorphous water ice, a structure in which molecules are disordered and contain trapped gases within their matrix. When heated beyond a threshold, amorphous ice can transition to a crystalline state, releasing its trapped gases in a sudden and sometimes explosive outburst. But such transitions typically occur closer to perihelion. If they were responsible here, they were happening in deeper layers or under conditions unlike those seen in solar-borne comets. Dust measurements complicated the picture further. The size distribution of grains appeared skewed. Instead of predominantly large particles, observation teams found a growing proportion of fine dust, tiny grains easily lifted by even modest sublimation. This shift indicated that whatever process was occurring favoured fragmentation of internal material into smaller pieces, perhaps due to structural breakdown of the nucleus. The presence of such fine grains enhances brightness disproportionately as they reflect light efficiently, meaning even small increases in dust production could dramatically raise the comet's luminosity. As teams compiled their findings, a pattern emerged not of resolution, but of multiplicity. Every dataset pointed to an underlying behaviour inconsistent with solar system norms. Whether through gas production, curves, dust morphology, or spectral fingerprints, 3I Atlas seemed to be governed by internal processes triggered indirectly by solar heating. It was as though perihelion had awakened something within, but only as the object retreated did the effects mature into visible form. Astronomers working with thermal models noticed that the object's insulating dust mantle, thin but present, could permit heat to seep downward only slowly. As deeper layers warmed, their reactivity intensified, triggering volatile release from pockets or channels that had remained sealed for millions of years. If these pockets existed at significant depth, then a delayed cascade of sublimation could indeed occur. But again, the magnitude remained difficult to reconcile. Meanwhile, particle tracking models of the tail revealed subtleties in how dust dispersed. The tail's curvature suggested not just solar radiation pressure, but variations in particle velocities over time hinting at changing jet behavior. Jets that activated only after perihelion, driven by shifting internal pressures, could explain some of the unexpected luminosity. Still, no single explanation satisfied all the evidence. The data told a story of layered complexity, a nucleus with unfamiliar chemistry, a surface reacting to sudden thermal gradients, deeper regions awakening from interstellar slumber, and structural tensions amplifying fragment release. Each piece contributed a verse to the unfolding puzzle, but none completed the song. What the world now observed was not the typical decline of a solar-warmed comet, but the prolonged crest of something much stranger, an unfolding event orchestrated by processes whose origins lay not in our sun's domain, but in another star's forgotten nursery. Each new measurement offered an insight, yet each also deepened the question. And so, as the light curve continued its unexpected climb, the universe's quiet message grew clearer. The data did not merely describe an anomaly. They described a story still being written layer by alien layer in the cold expanding halo of 3I Atlas. As the figures accumulated, photometric points rising gently, then insistently on graphs pinned to chalkboards, and glowing on monitors across observatories, the brightest anomaly of 3I Atlas began to take shape. Not in isolated data streams, but in the slow, collective realization that its light curve was behaving like a question that grew sharper each time someone tried to answer it. The curve itself had become the mystery, and in the long patient labour of astrophysics, few things are as revealing or as unsettling as a plot of brightness versus time that refuses to obey. Night by night, astronomers extended the line. They watched the faint haze surrounding the interstellar nucleus swell, responding to forces that should have been weakening rather than strengthening. The trend persisted with a steadiness that could not be dismissed. When the object had been only days past perihelion, some attributed the anomaly to delayed heating or residual activity common in long-period comets. But as weeks passed, the slow climb became unmistakable, forming a curve that bent upward with a strangely deliberate grace. Too persistent to be a glitch, too subtle to be explosive. The mystery lay in that shape. Cometary light curves rise and fall like tides under gravitational influence. They surge before perihelion dip afterward, occasionally stumbling into outbursts or fragmentation events. But they do not rise again without provocation. And yet 3I Atlas continued its strange ascent, the brightness intensifying with each new measurement, as though some unseen hand were lifting it into prominence. Comparisons with classic comet behaviour only deepened the contradiction. The slope of the increase was neither sharp enough to be an outburst, nor shallow enough to be random noise. It occupied a liminal zone, a region of behaviour where normal models strain, bend, and finally snap. Some comets show post-perihelion brightening due to rotational effects or structural collapse, but those typically manifest as irregular jumps, not as elegant continuous curvature. 3I Atlas was smooth, almost patient. Its evolution unfolded with the kind of slow inevitability that suggests underlying physics, not chaos. As analysts revisited the early arc of the curve, they noticed that the brightening hinted itself almost immediately after perihelion, though faintly. A gentle hesitation in the decline, a flattening of the expected downward slope. But the real rise began later as the object drifted into decreasing solar flux. This implied a decoupling between solar heating and the resulting activity, a lag that could only be explained by processes inside the nucleus taking time to propagate, to gather strength, to reach critical thresholds. And this lag was the first true escalation. It suggested layers. Layers not merely of ice but of history. Some models simulated the propagation of thermal waves through a nucleus, shaped by another star's processes, one that might contain stratified deposits of volatiles, unknown or exceedingly rare in the solar system. In such simulations, the sun's heat penetrates only gradually. The outer layers warm and cool quickly, but deeper regions require time. A passage around the sun would act not as a trigger, but as a catalyst initiating sluggish transformations that reach their peak only after the object is already retreating. To test this, teams plotted the derivative of the light curve, its rate of change. Here the escalation became stark. The brightness wasn't simply rising, the rate at which it rose was increasing. A second derivative curve curved upward with near-organic smoothness, suggesting feedback, a process that reinforced itself, a chain reaction of sorts, but one limited to the modest energies available in volatile sublimation. In some models, as deeper layers warmed, they released gases that fractured overlying crust, exposing fresher material which then sublimated faster. This feedback loop would explain the increasing activity while cooling occurred. but it also required a fragile architecture, one easily disturbed by heat and vulnerable to collapse. And an interstellar object aged by cosmic rays and micrometeoroid impacts would indeed be fragile. The tale of 3I Atlas offered a complementary clue. Dust dynamic models showed that the acceleration of small grains increased subtly after perihelion. This indicated more high-velocity material being emitted than before, suggesting that jets or vents were opening progressively rather than declining. More jets meant more active regions, and more active regions meant an expanding surface area of sublimation. The brightness rise matched this interpretation, a comet waking up late as if the sun had struck a deep chord that only now reverberated outward. Yet even this was insufficient to explain the scale. Many proposed internal phase transitions, chemical or structural changes triggered by exceeding certain temperature thresholds. Amorphous to crystalline ice transitions could account for sudden gas release, but again the timing felt wrong. Others invoked super volatile ices, nitrogen, oxygen, even argon latent from the environment of the star where 3I Atlas formed. These substances, only weakly bound, could begin to vaporize at much lower temperatures than familiar ices. But why would they not activate sooner on approach to the sun? Why wait? The greatest escalation came when data from several nights indicated that the shape of the light curve was beginning to deviate even further from expectations. Instead of rising exponentially, a hallmark of runaway sublimation, it shifted into a higher power polynomial form, a curve whose upward drift carried hints of structural or rotational changes. This was the moment when astronomers realized that the mystery was not static. It was evolving, growing more extreme, becoming more challenging to reconcile. Rotational dynamics entered the discussion. If the nucleus had begun to spin faster due to jet torque, a common phenomenon in active comets, then previously shaded regions could become exposed to sunlight, triggering new jets and new dust ejection. A gradual spin-up would shift the activity pattern in ways that could create a multi-phase light curve, where brightness increases not solely due to heating but due to geometry. This might explain why eruptions seem to switch locations or intensify collectively, but the rotational model introduced its own puzzle. A small nucleus under the stress of increasing spin might cross the threshold of rotational breakup. This could have produced observable fragmentation events, but the data revealed no major split. Only hints of small-scale debris suggested microfragmentation, rather than catastrophic disintegration. And such microfragmentation, if steady, could indeed produce the smooth curve observed. Tiny pieces breaking off, exposing fresh surfaces, sublimating vigorously. A slow-motion unraveling rather than an explosion. Or perhaps the object's unique chemistry fostered reactions invisible in standard comets. Cosmic rays striking the nucleus over millions of years in interstellar darkness could have induced chemical transformations, stored energy, awaiting release when warmed. When those molecules began to rearrange or decompose, they might release gases without requiring intense heat, powered instead by the release of potential energy trapped in altered compounds. This process could be slow, continuous, and self-enhancing, fitting the curve with eerie precision. Each hypothesis added a new layer, but none dispelled the sense that 3I Atlas was performing something alien, something not captured by equations shaped solely by solar-born comets. The rising light curve had become a lantern illuminating the boundaries of scientific knowledge. It told researchers that the object was not simply reacting to sunlight, but unfolding through its own internal logic, a logic inherited from a distant star system, a chemical and structural memory, carved long before our sun existed. And as the anomaly deepened, the narrative shifted from confusion to recognition. 3I Atlas did not merely break rules. It revealed them to be local approximations, not cosmic truths. Its brightness curve was not misbehavior. It was the echo of an origin story written far away, now playing out in the cold, expanding halo around one small interstellar traveler. The deeper scientists probed into the reasons behind 3I Atlas's rising luminosity, the more the conversation drifted toward the most delicate and unpredictable domain in cometary science chemistry. Not the familiar chemistry of a water ice sublimating under sunlight, nor even the more volatile dance of carbon monoxide and carbon dioxide. Those signatures had been glimpsed clearly enough, and explained only a fraction of the strange behavior. What puzzled researchers most was the possibility that 3I Atlas contained materials scarcely found, or even entirely absent in comets born within the Sun's protoplanetary disk. It was here, in the realm of exotic ices and deep interstellar residues, that the mystery's heart began to pulse. The first clues came from the object's spectral lines. Though faint and often masked by dust-scattered light, certain ratios hinted at an unusually rich presence of super-volatile compounds, molecules that evaporate at temperatures barely above absolute zero. Nitrogen ice, carbon monoxide ice, even traces of methane clathrates were tentatively suggested in the earliest analyses. But these hints raised their own riddles. Supervolatile ices tend to sublimate explosively during solar approach, releasing gases rapidly and dramatically. Yet 3 Atlas had not erupted dramatically at perihelion. It had passed that fiery point with restraint only to begin its enigmatic brightening afterward. This timing demanded an explanation rooted not in the sun's heat itself, but in the relationship between heat and the material it touched. Researchers revisited thermal models and discovered a possibility. What if the key was not the warming but the cooling? What if exotic ices formed under conditions unique to another star's frigid birth environment were sensitive not to the increase in heat, but to the gradient of heat's disappearance? In other words, what if cooling activated processes that heating alone did not? Some ices exhibit this behavior. Certain molecular bonds become metastable during a warming phase, reorganizing into unstable configurations that remain dormant until temperatures begin to fall. Once cooling begins, these strained bonds can break apart, releasing gases trapped for millions of years. The release is not explosive but progressive, a slow unraveling of stored energy. If 3I Atlas possessed such compounds, then its post-perihelion brightening could reflect not sublimation, driven by solar heat, but the delayed activation of reactions triggered only after the sun's influence receded. Other theories focused on Interstellar, layering the idea that 3I Atlas might contain strata of material accumulated throughout its expulsion from its home system and its long drift through the galaxy. Cosmic rays starlight and the diffuse chemical haze of interstellar space could deposit unusual molecules onto its surface, or alter the chemistry of its uppermost layers. Some of these layered materials could act as catalysts, accelerating chemical reactions, once the nucleus began to contract during cooling. A particularly intriguing hypothesis involved the conversion of amorphous ice to crystalline ice. Amorphous ice formed at extremely low temperatures is porous and capable of trapping significant amounts of gas within its chaotic structure. When warmed, it begins to rearrange into a more orderly crystalline form, releasing trapped gases in the process. But the transition does not occur uniformly. It depends on local temperature variations and the presence of impurities. If 3I Atlas contained layered regions of amorphous ice buried beneath dust and more stable ices, then heat from perihelion might have reached those layers only after a considerable delay. Once triggered, crystallization could propagate inward or outward, releasing gases steadily rather than catastrophically. This process could easily produce a gradual and sustained increase in activity, precisely the kind observed. Yet even this explanation did not fully capture the magnitude of the brightening. The amount of dust and gas released and the duration of the increase suggested a more potent internal transformation. It was then that researchers considered something more extreme, the presence of interstellar supervolatiles, created not during planetary formation, but during the object's long interstellar voyage. Cosmic ray bombardment can fracture molecules, creating radicals, highly reactive species with unpaired electrons. Over millions of years, these radicals can accumulate in pockets within the ice. In stable, ultra-cold interstellar conditions, they remain inert. But once warmed and subsequently cooled, those radicals can recombine or release stored chemical potential in a slow, controlled manner. If 3I Atlas harboured such cosmic ray-forged compounds, then its behaviour after perihelion could be understood as a gradual chemical awakening. Not an explosion, not a burst, but a steady unwinding of reactions that had lain dormant since the object was ejected from its home system, perhaps during a gravitational disturbance or the death of its parent star. Yet even within these chemical explanations, deeper ambiguities remained. The interplay between heat structure composition and rotation created a complex web of possibilities. Some models suggested that exotic ices closer to the surface vaporized first, weakening the overlying dust mantle and exposing deeper layers to sunlight. Others proposed that as the object cooled, it contracted unevenly, cracking open subsurface pockets of supervolatile material that had been sealed since the formation of its parent system. Another question emerged: what if the behavior was not purely chemical, but partially physical? If the interstellar object had experienced micrometeoroid impacts during its journey, tiny collisions that accumulated over eons, its surface might be riddled with fractures each filled with dust or volatile material. Such microfractures could create a network of channels through which sublimated gases might migrate, altering the surface pressure dynamics and producing localized jets only after perihelion. The result would be a hybrid mechanism chemical activation supported by structural pathways. The discussions grew increasingly complex. Some scientists questioned whether 3I Atlas had ever been a typical comet. Perhaps it was the fragment of a larger body torn from a planetesimal or icy dwarf during early planetary formation in its home system. Such fragments could contain unusual mixtures of primordial compounds born from regions of the disk, far colder or far more chaotic than anything in our solar system. If its birth environment was richer in nitrogen or carbon-based ices, the object might behave unlike any known solar comet, especially under thermal stress. The light curve, once merely puzzling, now resembled a fingerprint of alien geology. Its rising brightness became a coded message written in evaporating molecules, crystalline transitions, radical recombinations, and fragile layers of interstellar frost. Each possibility carried implications that reached far beyond this single object, brushing against fundamental questions about how planetesimals form around other stars, how they evolve, and what chemical libraries they carry across the galaxy. For as scientists sifted through hypotheses, one implication loomed above all others. If 3I Atlas held exotic chemistry unseen in solar comets, then interstellar objects might not be occasional anomalies. They might be windows, small icy drifting windows into the diversity of planetary systems across the Milky Way. In their strange brightening, their delayed reactions, their alien transitions, they might reveal the unseen architectures of worlds older and colder than our own. And as 3I Atlas continued its slow, luminous bloom, scientists realized they were no longer tracing the life of a mere comet. They were tracing the echo of another star embedded in the chemistry of an object, now drifting outward into darkness, glowing more brightly the farther it retreated from the sun. The more astronomers studied 3I Atlas, the more they began to suspect that its strange post-perihelion brightening might not originate solely from exotic chemistry or delayed thermal processes. Increasingly, a whisper circulated through research teams. Perhaps the object was breaking apart quietly, gradually and visibly at first, and that this subtle fragmentation was feeding the rising luminosity. Fragmentation is no stranger to cometary science. Countless solar system comets have revealed their fragility when approaching the sun. But with 3I Atlas, the idea carried a uniquely unsettling weight. This was not a familiar native of our cosmic neighbourhood. This was an interstellar wanderer, ancient and alien, its materials shaped by processes that unfolded under a different star's early light. If it was fragmenting, it was doing so according to rules astronomers had never seen. At first the signs were ambiguous. No large pieces separated cleanly from the nucleus, nothing obvious, nothing traceable across multiple images. But very gradually astronomers noticed faint hints in the morphology of its coma. In some frames, subtle asymmetries crept into the otherwise smooth, diffuse glow. A faint bright patch would appear on one night shift, slightly on the next, then dissipate. These were not solid detections. They were murmurs in the dust, the kind of signatures that could be noise or could be something far more consequential. Yet as the anomaly persisted, the patterns accumulated. When teams compared high-resolution images across several nights, they observed minute irregularities in the inner coma's brightness distribution, small, concentrated regions of dust that did not align with expectations from jets alone. Rather than emerging from discrete vents, these clouds appeared more diffuse, as if born from the disintegration of fragile material, spread across the nucleus's surface. The idea took shape: microfragmentation, the steady shedding of small chunks or grains that once freed quickly sublimated or crumbled into dust. This process could account for the smooth brightening. Microfragmentation does not occur explosively. It spreads across time like a slow unraveling, each tiny piece contributing slightly to the overall luminosity. And because fresh surfaces are constantly exposed through this gentle decay, sublimation can intensify even as the object moves farther from the sun. The brightness curves smooth. Rising devoid of spikes fit this behavior eerily well. Thermal stress offered a compelling trigger. As 3I Atlas passed perihelion, differential heating likely created fractures across its nucleus. Interstellar objects bombarded for eons by cosmic rays may have developed deep structural weaknesses. These microfractures would not be visible, yet they could destabilize the nucleus just enough that cooling afterward caused brittle materials to shrink unevenly, prying open tiny gaps. Each crack would expose interior ices, each exposed surface would sublimate, and each sublimation event would nudge dust into space. Thus the process would amplify itself. A small fracture exposes fresh material. That material warms sublimates and erodes. Erosion expands the fracture. More material is released. The feedback loop intensifies. The nucleus begins to crumble, not catastrophically but delicately, peeling itself apart layer by layer. For many, this explanation resonated with eerie familiarity. They remembered the behavior of some solar system comets such as Shoemaker-Levy 9 or C2012 S1 Ison, whose brightness surged before disintegration. Yet 3I Atlas was different. Its brightening was not a prelude to a visible breakup. Weeks passed, then longer, and still the core remained intact, at least as far as observations could tell. Fragmentation had to be happening on a scale too fine for even the best telescopes to resolve. Dust modelling provided further support. When scientists analysed the scattering properties of 3I Atlas's dust, they found that fine particles increasingly dominated the coma, a signature consistent with the gradual breakdown of surface materials rather than the abrupt release from jets. These tiny grains reflect sunlight more efficiently than larger ones, meaning that even small increases in their abundance lead to dramatic rises in apparent brightness. The dust distribution skewed toward the smallest particles suggested an ongoing fragmentation cascade. As these analyses deepened, theories emerged involving the nucleus's possible internal structure. Perhaps 3I Atlas contained layers of different densities regions, where compacted ices abutted much looser aggregates. As the object warmed and cooled, the compressions and expansions of these layers could tear them apart from within. This idea gained traction when dust velocities were measured. The speeds were too low to be driven purely by strong sublimation jets. Instead, they matched the gentle release one would expect from crumbling interior material drifting outward. Rotation added yet another complication. If 3I Atlas was spinning, perhaps slowly, perhaps unevenly, thermal stresses and centrifugal forces could combine to undermine its integrity. A weak or porous object, especially one shaped by interstellar radiation and freezing processes, might have reached a point where certain regions could no longer sustain their structure under rotational stress. Even a slight spin-up could push it toward disaggregation. Yet no major fragments were observed, a clue pointing not to catastrophic rotational breakup, but to a more nuanced phenomenon: localized shedding. Localized shedding becomes plausible if the nucleus's surface is irregularly shaped or contains ridges and cliffs. Temperature shifts would affect these regions differently, creating uneven stress and causing small-scale collapses. The dust released from such collapses, however subtle, would disperse rapidly and blend into the coma, contributing quietly to the overall brightening. Another idea, inspired by the behavior of 2I Borisov, emerged: fragmentation shadows. In Borisov's case, tiny fragments peeled off before the major breakup event, producing an amplified brightness that researchers initially mistook for increased sublimation. For 3I Atlas, fragmentation shadows could explain minor transient bright spots appearing within the coma features, too faint to be definitive on their own, yet collectively suggestive of ongoing microfragmentation. What set 3I Atlas apart, though, was the timing. Most comets fracture near perihelion, the moment of greatest stress. This object waited. It endured the heat, then unraveled in the cooling aftermath. Cooling-induced fragmentation is not well understood, but the idea gained traction. Contracting layers could behave unpredictably, especially in a nucleus formed under another star's chemistry, where structural bonds might weaken or shift in ways unfamiliar to scientists on Earth. And as researchers pondered these possibilities, an uncomfortable realization emerged: if 3I Atlas was fragmenting silently, the event was irreversible. A fragmented nucleus does not reassemble. Its interior secrets would be revealed only through dust, not through intact structure. And as it drifted farther into space, the fragments would disperse into nothingness. A story written in brittle ice and cosmic dust would dissolve into the darkness, leaving behind only the rising brightness curve and the tantalizing traces woven into its fading halo. Fragmentation, then, was not merely a mechanical process. It was a narrative one of decay, revelation, and impermanence. And for many astronomers, it suggested that the brightening of 3I Atlas was not a flare of life, but a quiet undoing, a release of ancient materials that had survived a journey of millions of years, only to crumble under the gentle touch of another star. The mystery deepened further, but the path grew clearer. Something within the nucleus was failing, and in that failure the comet was telling its story. As the mystery of 3I Atlas deepened its brightness, rising, its dust subtly reshaping its inner processes, awakening in defiance of solar distance, a different line of inquiry began to form, quiet at first, then gradually gaining gravity. If this object behaved unlike any comet known in the solar system, perhaps the explanation did not lie solely in what it was doing now, but in what it had been before. The nucleus's delayed reactions, its exotic chemistry, its fragile architecture, all these might be symptoms of a far older story. And so astronomers turned their attention backward away from the sun's influence, and toward the dark, forgotten reaches of interstellar space, where 3I Atlas had spent nearly all of its existence. For millions, perhaps billions of years, the fragment had drifted alone through the galaxy, a silent shard carrying the cold memory of the system that cast it out. Interstellar space is not a true void. It is a vast ocean threaded with faint radiation, scattered particles, cosmic dust flows, and the endless bombardment of high-energy cosmic rays. Over ages beyond human comprehension, these forces sculpt the surfaces and interiors of passing objects. They alter ices, crack minerals, rearrange molecules, and frost entire surfaces with residues of carbon and nitrogen. The universe, in its quiet way, writes on every wandering stone. For 3I Atlas, the writing may have begun long before it entered our system. Much depended on how it was born. Every planetary system begins as a disk, a swirling turbulent expanse of gas and dust encircling a young star. Within this disk, temperatures vary dramatically. Close to the star, heat strips away volatile compounds. Farther out, cold allows them to condense. In our solar system, this gradient shaped everything from Mercury's scorched surface to Pluto's frozen plains. But not every star forms with the same disk composition. Some form from clouds rich in nitrogen, others from dust abundant in carbon-oxygen or metallic grains. Some bear dense reservoirs of ammonia or methane, others thin traces of organics. In such diversity lie the seeds of unimaginable variety. If 3I Atlas formed in a disk richer in nitrogen-based ices or exotic carbon compounds, then its behavior under solar heating would reflect those differences. Supervolatiles like nitrogen, oxygen, or hydrogen cyanide would behave unpredictably under thermal gradients unfamiliar to solar system comets. They might migrate inward over time, forming deep reservoirs that activate only when exposed through structural collapse. Or they could crystallize under certain pressures, forming weak layers that fracture easily during cooling. But the object's origin might have been even more dramatic. Some interstellar fragments are believed to come from the violent early histories of planetary systems, moments when giant planets migrate inward or outward, destabilizing vast fields of planetesimals. Others may be cast off during close stellar encounters, when gravitational tides shred disks and fling their debris into interstellar exile. If 3I Atlas had been part of such an environment, it could have endured heating, cooling compression, and impact events long before the sun ever touched it. These early experiences might have created the layered, unstable, chemically reactive structure, now glimpsed through its rising brightness. And then there is the long journey. Once ejected, an interstellar body enters a realm where cosmic rays dominate. These high-energy particles pierce the nucleus-breaking chemical bonds, rearranging molecules and producing complex organic residues. Over millions of years, cosmic irradiation can create thick crusts of carbon-rich material, insulating the interior while subtly altering it. Laboratory experiments simulating cosmic ray exposure produce ices that behave strangely under temperature changes, ices that crumble, fracture, or release gases unpredictably when warmed or cooled. If 3I Atlas carried such radiation-forged compounds, then the sun's touch might have acted less like a gentle warm breeze and more like a catalyst awakening deeply altered chemistry. Some researchers took this idea further. They proposed that 3I Atlas might have originated near the snow line of its home system, an unstable region, where volatile condensation and early heating events produce fragile structures with trapped gases nested deep within. Such regions are prone to chaotic chemistry, where batches of material form with wildly different properties. If the object were forged there, its interior could easily contain layers of exotic compounds unfamiliar to Earth-bound laboratories. Others looked at the dust itself. Interstellar dust grains carry the fingerprints of distant stars. Their composition, metallic silicate carbonaceous, depends on the generation of stars that produced them. If 3I Atlas condensed from such material, its dust might scatter sunlight differently, contributing faintly to the unusual brightness slope observed in its light curve. But more intriguingly, its dust could reflect the temperature and pressure conditions of a star system very different from our own. Dust models hinted at smaller average particle sizes than those seen in solar comets. This suggested a formation environment where processes like grain coagulation or frost deposition had unfolded in an entirely different sequence. But the most profound question concerned its internal architecture. Millions of years drifting through interstellar cold would cool the nucleus to temperatures far lower than anything typical in our solar system. In such a prolonged deep freeze, ices undergo transformations not normally seen. Hydrogen molecules can embed themselves into crystalline lattices. Radical species formed by cosmic rays can accumulate in dormant pockets. Weakly bound volatiles can migrate slowly through the interior, forming lenses or veins that awaken only when reheated. These processes could produce a nucleus unlike any comet known, layered, brittle, chemically restless, perhaps even containing ancient interstellar frost that had never once been exposed to a star's light until now. And so as the sun warmed 3I Atlas, the object might have responded not like a solar comet, but like an alien archive, its chemistry unlocking sequentially each layer, reacting differently to the thermal pulse. In this emerging narrative, the brightening was no longer merely a post-perihelion puzzle. It was an act of memory. The object was reenacting the history of its formation layers, warming at different rates, cracking at different thresholds, releasing gases shaped by a star that may have long since died. Each increment of brightness was not simply sunlight reflected from dust. It was an echo of a distant star's chemistry, a whisper from a planetary disk that existed long before our own. This idea, interstellar memory, did not claim that 3I Atlas was alive or conscious. Rather, it recognized that physical materials carry their past with them. A stone remembers its formation in the structure of its minerals. A comet remembers its origin in the distribution of its ices. An interstellar fragment remembers a world we will never see in the way its dust glows and shatters under a foreign sun. Through this lens, the rising brightness of 3I Atlas became a form of storytelling. As it drifted outward, shedding material into the dark, the object revealed not only what it was, but where it came from. The mystery did not diminish. It grew richer, more expansive, stretching beyond the sun's influence into the deeper, older history of the galaxy itself. And astronomers realized with quiet awe that in 3I Atlas they were not merely observing a comet's response to sunlight. They were witnessing the unfolding autobiography of a fragment older than humanity, older than Earth, older even than the patterns of chemistry our solar system taught us to expect. The nucleus was speaking in the only language it knew, light dust gas and the slow unraveling of memory drifting back into the cold from which it came. As scientists grappled with the chemistry, thermal lag, and interstellar memory encoded within 3I Atlas, their attention gradually shifted toward another possibility, one that blended physics motion and light into a single elegant framework. The rising brightness could be explained if the object were not simply releasing gas, but channeling it, shaping it, directing it with a symmetry. This would transform the comet from a passive sublimator into an active engine, with jets behaving not merely as byproducts of heating, but as sculptors of both motion and luminosity. Such dust engines, as some researchers called them, were known in the solar system. Sublimation does not occur evenly across a comet's surface. It emerges through vents, cracks, and fractures, each acting like a microscopic rocket nozzle. Gas streaming from these points can push the nucleus, altering its trajectory. This phenomenon was invoked to explain the anomalous acceleration of Oumuamua, an interstellar object that drifted off its gravitational path without visible signs of jets, leaving scientists to imagine the faintest, most subtle thrusts invisible to telescopes. 3I Atlas, however, was not subtle. It was brightening in a way that suggested dust jets were not just present, but evolving, multiplying, intensifying, and perhaps reshaping the very structure of the nucleus. These jets did not operate in isolation. They interacted with rotation thermal gradients and structural weakness, And in this synergy, the mystery of 3I Atlas found new depth. In images of the coma, faint plumes hinted at anisotropic gas flow, meaning jets pushed material unevenly. Some were strong enough to carve faint transient wings along the coma's edges. Others sent fine grains into space at high velocities. Such behaviour, subtle but detectable, suggested the presence of localized thrusts. These thrusts could shift as the object spun, causing jet directions to change over hours or days. If 3I Atlas rotated with any irregularity as most comets do, its jets would illuminate different parts of the nucleus, as the object turned, exposing fresh surfaces to sunlight and activating new vents. This would create a cascade. The more it rotated, the more jets awakened, and the more jets awakened, the more dust was released. This feedback mechanism could produce a long, smooth rise in brightness, a slow ignition of activity driven not by the sun's proximity, but by the choreography of jets and rotation. Dust jets also produce far more light than gas alone. Dust, particularly the fine grains implied by spectral analysis, reflects sunlight with astonishing efficiency. Even small increases in dust mass can cause disproportionate brightening. A single newly active jet could double the dust output, shifting the brightness curve dramatically. If multiple jets awakened in sequence, the effect would blend into the rising slope observed. Some scientists modelled the possible spin states of 3I Atlas. A nucleus elongated or irregular could wobble its rotational poles, shifting due to torque from asymmetric jets. This non-principal axis rotation, commonly called tumbling, can destabilize a nucleus already weakened by cosmic ray damage and interstellar aging. A tumbling object exposes surfaces to solar heating, unpredictably creating complex patterns of sublimation. Such rotational instability could also amplify fragmentation. If a weak region spun into sunlight repeatedly, it might erode faster than surrounding areas, shedding dust and microfragments. These fragments could either drift away or fall back onto the surface, altering local albedo or insulating material in ways that modulate future sublimation. The result would be a constantly changing jet landscape, a comet whose activity evolved as its surface danced between light and shadow. Dust jets also produce what scientists call rocket forces. These forces push the object subtly but measurably, changing its trajectory. The magnitude of these changes depends on the mass, direction, and duration of the jets. In some cases, the jets can significantly modify the orbit over time. Though 3I Atlas travelled on a largely hyperbolic path dictated by interstellar speed, subtle deviations from its predicted trajectory raised eyebrows. They were not large enough to be definitive, but they were consistent with dust-driven forces. This insight led to a provocative idea, perhaps. 3I Atlas was not just brightening. Perhaps it was steering, responding to jets with motion and structure in ways that compounded the brightness curve. The nucleus might be twisting, shedding dust in different directions, exposing new surfaces at precisely the right angles to sustain high reflectivity. The shape of the tail provided further support. Dust models indicated that the curvature of the tail shifted subtly over time, implying a changing dust emission pattern. Traditional solar system comets show tail variations that correlate with daily heating patterns or rotation. But 3I Atlas displayed shifts that did not align with simple solar geometry. Instead, they hinted at evolving internal activity, new jets turning on old jets, fading dust engines modifying their thrust lines in slow harmony with the object's cooling. As simulations grew more sophisticated, some researchers proposed that the object's surface might include pockets of extremely fine material, interstellar frost or cosmic ray processed dust, that could be lofted by even mild jets. If so, the brightening could represent not increased sublimation, but increased dust lofting efficiency. A small jet could lift a disproportionately large amount of dust, reflecting more sunlight. This pushed the thinking beyond ordinary sublimation physics toward a realm where dust dynamics and internal structure intertwined. A fragile nucleus riddled with microvoids, or layered with fine powders deposited over millennia of interstellar drift, could behave like a dust reservoir. The sun warming the object during perihelion might activate jets that then swept across this reservoir, releasing dust in waves, triggered not by heat, but by structural collapse and jet erosion. And if these jets were uneven, if they carved their way across the nucleus unpredictably, then the brightening could grow sharper as the dust layers thinned, their release becoming easier with each subsequent activation. Some even modelled it as a dust engine cascade, a process where jet activity exposes deeper material, which then sublimates faster, which then accelerates rotation, which then exposes still more material. This kind of cascading feedback could create multi-week brightening without ever appearing explosive because each individual step is small, but the cumulative effect is profound. Yet even these ideas, rich and complex as they were, did not fully resolve the mystery. They merely shifted its weight from chemistry to structure, from structure to jets, from jets to motion. In this interplay, 3I Atlas became less a single phenomenon and more a system, a dynamic machine shaped by forces acting in delicate balance. And as the dust engines whispered through space, pushing, spinning, lifting and brightening, astronomers realized they were witnessing the delicate mechanics of an interstellar traveler, revealing its nature not through words, but through the choreography of dust and light. It was not merely brightening, it was unfolding. A slow mechanical poetry written in jets and shadows drifting along a path millions of years long. As astronomers traced the intricate interplay of jets, dust and interstellar memory within 3I Atlas, another possibility grew increasingly difficult to ignore, one that reached deeper than chemistry, deeper than jets, deeper even than cosmic ray-altered ices. Many began to consider that the true driver of the object's rising luminosity might lie within its interior, a fragile architecture of ancient ices and volatile reservoirs destabilized by the profound thermal shock of passing near a star for the first time in millions of years. In this view, 3I Atlas was not merely reacting to sunlight, it was suffering from it. Internal instability, long theorized but rarely observed directly, could explain the strange delay in activity. When the sun's heat first bathed the interstellar fragment, the warmth would have penetrated only shallow layers. But beneath the surface, beyond the reach of direct solar heating, lay volumes of pristine ultra-cold material untouched since the object's formation. These inner reservoirs might respond not immediately but slowly, as heat diffused inward by conduction. And once these deep regions reached transitional temperatures, structural and chemical changes could propagate through the core, unleashing delayed bursts of gas that pushed dust outward only after perihelion. In thermal models, such delayed responses produce activity curves that mimic what astronomers observed, a brightness peak occurring not at closest approach, but later when internal heating catches up. Yet, in the case of 3I Atlas, the scale of brightening suggested far more than delayed sublimation. It hinted at instability, an interior losing integrity, evolving toward collapse. One possibility involved amorphous ice, a disordered solid that forms in ultra-cold environments. Amorphous ice traps gases within its structure, locking them in chaotic matrices. When it warms, it transitions sharply to crystalline form. This transition releases trapped gases in a process that can crack, fracture, or even explosively disrupt the surrounding material. If large regions of 3I Atlas consisted of amorphous ice formed under extreme interstellar cold, then perihelion would have initiated a slow transformation. But the transformation might only propagate inward after cooling began, when outer layers contracted, placing stress on already weakened crystalline boundaries. This would mean the brightening after perihelion reflected the interior's belated rearrangement, the crystalline wave moving inward, releasing gas unevenly, opening cavities, and pushing dust outward in a long, slow surge. Some researchers describe the process as a thermal fuse, a chain reaction ignited by the sun but delayed by the object's unique insulating properties. Another possibility invoked volatile migration. In extremely cold environments, certain ices migrate slowly under temperature gradients flowing away from warmth or toward pressure minima inside the nucleus. On approach to the sun, warming outer layers could have driven volatiles deeper inward, creating an overpressurized core. Then, as cooling resumed post-perihelion, those volatiles could reverse direction or begin expanding as crystallization set in, cracking open caverns and releasing gas in pulses. Such high-pressure pockets sealed for millions of years would need only slight structural shifts to rupture, allowing sublimating ices to escape in slow but powerful waves. Models predicted that such ruptures would produce exactly the kind of brightness curve observed, smooth, sustained, and intensifying. But structural instability could also originate in the material strength of the nucleus itself. Comets are fragile even in the solar system. Interstellar comets are likely more so. Over millions of years, cosmic ray bombardment can break molecular bonds within ice, softening the matrix and creating brittle zones scattered throughout the core. Micrometeoroid impacts accumulate, drilling tiny cavities and weakening structural cohesion. The repeated cycles of freezing and annealing in interstellar space can create internal voids pockets, left by sublimated material that condensed elsewhere. These voids might remain stable at ultra-low temperatures, but when exposed to solar heat they would contract, deform, or collapse. A single collapsing void could trigger adjacent collapses in a process akin to subsurface cave-ins. Dust and gas trapped in these voids would escape slowly through emerging cracks, feeding the coma with a continuous supply of fine particles. Such a mechanism would produce neither catastrophic disintegration nor sudden outburst. Instead, it would produce exactly what astronomers saw: a smooth, persistent brightening curve driven by the slow unraveling of interior architecture. There was even the possibility of an internal avalanche, a metaphor borrowed from geophysics. In this scenario, once interior collapse begins, it propagates through weak layers, fragmenting outer crusts and exposing new surfaces that sublimate vigorously. Buried ices might slide or sink, dragging dust with them and altering internal stress fields. Each minor collapse would momentarily increase activity. Together they would appear as a continuous rising brightness. Rotation could play a critical role here. If 3i Atlas was spinning even slowly, the centrifugal force might exacerbate internal stresses. A weak nucleus under rotational strain could experience shear forces stretching fragile layers horizontally. When heat caused differential expansion between layers of varying composition, fractures could form radially or laterally. The interaction between rotational stress and thermal shock would accelerate fragmentation in unpredictable ways. Tumbling, if it occurred, would worsen this. Tumbling exposes different regions of the nucleus to sunlight at irregular intervals. Heating becomes uneven. Some regions warm quickly, others cool rapidly. Such chaotic cycling could tear apart layered material with different thermal expansion coefficients. The interior would not simply warm, it would warp. But chemical transitions might offer the most dramatic explanation. Cosmic ray-induced radicals trapped in interstellar ice matrices could recombine explosively at threshold temperatures. These reactions need not produce visible explosions. They could produce gas pressures that subtly inflate cavities, stretch crusts, and fracture overlying dust mantles. The recombination of radicals acts like a time-delayed release of stored energy, accumulated slowly over millions of years and released incrementally as conditions change. Some laboratory simulations support this. When samples of ice irradiated under interstellar-like conditions are warmed and cooled, researchers observe delayed gas release cracking and micro-explosions that continue long after the initial heating stops. These samples brighten under simulated sunlight even as temperatures fall. This behavior mirrors the light curve of 3i Atlas. If the nucleus contained multiple such zones, pockets of stored chemical stress, then perihelion would have awakened them like embers stirred by a passing breeze. Each pocket might transition at its own rate, releasing gas, lifting dust, reshaping the coma. The resulting light curve would be layered, multifaceted, and difficult to model precisely as observed. Some models also proposed phase changes between different crystalline structures of water ice, or transitions involving clathrate hydrates, molecular cages that trap gases like methane, ethane, or nitrogen. Clathrates disintegrate when warmed or depressurized, releasing their trapped gases. If present in significant quantities within 3i Atlas, they could have contributed to a slowly unfolding chemical metamorphosis driving the brightening. The deeper scientists explored these internal possibilities. The clearer one conclusion became: the behavior of 3i Atlas was not governed by the sun alone. It was governed by the memory of its origin, the transformations it endured during interstellar exile, and the shock of encountering a star after an eternity of cold. Sunlight had awakened something ancient, something fragile and unstable deep within the nucleus. The rising brightness was not merely a surface response, it was a symptom of profound change. 3i Atlas was not just brightening, it was evolving, coming undone, revealing layers of its past in the only way it could, through light dust pressure and slow internal collapse. And as the object drifted outward, the universe allowed observers one of its rarest gifts: a glimpse into the hidden interiors of a body that formed under another star, carrying within it the architecture of worlds beyond the sun's domain. By the time astronomers had mapped the rising brightness through chemistry jets and internal decay, a new tension settled across the scientific landscape, a growing awareness that the familiar tools of comet theory were bending under the weight of something they had not been built to explain. The data remained real, the behavior undeniable, the curve indisputable, and yet no conventional model, thermal, structural, dynamical, could fully stitch the observations into a singular, satisfying narrative. It was here at the edge of comprehension that the conversation began shifting toward hypotheses that stretched physics itself. Not fantasies, not fiction, but the kinds of theoretical frameworks usually invoked only when nature refuses to remain inside its expected borders. The first of these extreme explanations came from the study of outgassing efficiencies. Some researchers wondered whether 3I Atlas could be covered in a mantle of materials with sublimation energies dramatically different from any found in solar system comets. If its surface ices possessed extraordinarily low latent heats requiring very little energy input to vaporize, then the sun's influence could initiate cascades of sublimation far beyond standard models. Yet even this idea strained credibility. Materials that volatile should have erupted violently near perihelion, not waited to awaken afterward. Others suggested the possibility of a nucleus with a fractal interior, its solid body composed not of compacted ice, but of a tenuous porous network resembling the weakest aerogel. Such a structure, if shaped under exotic conditions in another planetary system, could allow heat to penetrate deeply and unevenly. In such a model, compressive waves triggered by solar heating could travel inward, bouncing through cavities, causing delayed and unpredictable reactions as energy propagated across irregular channels. As poetic as it sounded, this model raised serious questions about survival. Could a body so weak endure ejection from its home system? Could it withstand millions of years of interstellar bombardment? A more radical idea involved supercritical sublimation. In rare conditions, usually involving exotic volatiles or extremely porous media materials, can transition rapidly from solid to gas once specific pressure thresholds are crossed. If deep pockets inside 3I Atlas housed supercritical compounds held in metastable equilibrium, then minor thermal changes could release large volumes of gas in prolonged waves. But this hypothesis required a delicate balancing act of temperature and pressure unlikely to persist over interstellar timescales. Then came the gravitational hypotheses. Some theorists speculated that 3I Atlas could have passed near subtle gravitational influences, other small bodies perhaps on its inbound trajectory. Tiny changes in spin state could have amplified internal stresses, triggering behavior that only expressed itself after perihelion. But observational data showed no evidence of such encounters. The object's path through the inner solar system appeared clean. Another camp explored electromagnetic theories. Interstellar objects carry charge asymmetries accumulated during long exposure to cosmic rays and plasma fields. When entering the heliosphere, they encounter the sun's magnetic influence, a vast dynamic structure shaped by the solar wind. If 3I Atlas had an unusual charge distribution, interactions with the heliospheric magnetic field might have induced electrical currents heating localized regions or cracking surface layers. Yet while this effect is plausible, the magnitude needed to explain the brightening seemed too large for known physics. A more metaphysical sounding but scientifically grounded hypothesis involved quantum effects within the ice matrix. Laboratory studies have shown that certain low-temperature ices exhibit tunneling behavior, allowing molecules to shift positions through energy barriers they cannot overcome classically. In an interstellar nucleus frozen below 30 Kelvin for millions of years, such quantum reorganization could have formed unique structures that respond unpredictably to warming. As fantastical as this sounds, quantum tunneling in ice is well established. Whether it could produce the behavior seen in 3I Atlas remains uncertain, but it captured the imagination of physicists seeking mechanisms that could operate over cosmic timescales. Another emerging idea involved dust cohesion. Some models proposed that the tiny grains coating 3I Atlas were bound together by van der Waals, forces more delicate than those in typical comets, the result of different chemical compositions or interstellar processing. As thermal cycling weakened these bonds, dust could be released in a dramatic but smooth cascade. Such a cohesive collapse model could explain the gradual bloom in brightness, the outermost layers disintegrating grain by grain, each release triggering more instability beneath it. Yet the model lacked direct observational support. Dust cohesion on interstellar objects remains deeply uncertain. Then there were the dynamical theorists who proposed the idea of rotational bifurcation, a state where the object's spin becomes chaotic due to internal mass redistribution. If jets or sublimation shifted mass within the nucleus, its rotation could abruptly change, redistributing sunlight across different regions, and triggering sudden surges of activity. This would explain the changing morphology of the coma, and the evolving brightness. But again, the required coupling between internal instability and rotational chaos skirted the edges of what rotational models can reliably describe. Some researchers even revisited the puzzle raised by Oumuamua: could radiation pressure be playing a role? For a dust-rich fragment with low density, the push of sunlight could alter rotation orientation and surface exposure in complex ways, triggering unexpected activity. Yet unlike Oumuamua, 3I Atlas displayed clear signs of outgassing and dust production. It was a comet, not a smooth reflector. Radiation pressure alone could not account for its behavior. In one of the more daring proposals, scientists considered clathrate-driven phase explosions events where gas molecules trapped inside crystalline cages destabilize synchronously across vast regions. If 3I Atlas possessed large clathrate beds formed in the cold intricacies of an alien disk, their collapse could release gas continuously for weeks, producing the steady brightening observed. Laboratories on Earth have produced such phase transitions in controlled conditions, but scaling them to cometary dimensions requires assumptions that push current understanding. Some astrophysicists stepped back further still, asking if perhaps interstellar objects represent a category distinct from solar comets, not variations on a known theme, but truly separate geological species. In this view, 3I Atlas was not misbehaving. Rather, it was finally teaching humanity how objects from other star systems behave. If interstellar comets formed under extreme conditions laden with materials unknown on Earth, then their reactions to sunlight could easily appear exotic. Delayed brightening might be normal for bodies forged in certain types of disks. We simply lack the sample size to know. At the very edges of speculation stood the idea of multi-volatile oscillation, a model in which different ices within the nucleus activate in sequence, each unleashing conditions that trigger the next. This volatile cascade would create waves of activity, each stronger than the last. Intriguingly, the light curve of 3I Atlas resembled a long, gentle wave rising, cresting not yet breaking. Some saw this as the signature of a multi-phase awakening. None of these ideas solved the mystery. All strained physics to its edge, and yet none exceeded it. Each explanation hovered in that rare zone where science brushes against its own limits, where observations hint at new phenomena, and theories attempt to reach beyond their traditional boundaries. And in the end, this was the quiet truth: the universe had presented a puzzle too intricate for any single theory. 3I Atlas was not a contradiction. It was a reminder that the physics humanity knows is built upon local truths shaped by one star, one disk, one set of formative processes. Beyond the sun's cradle, the galaxy writes its own variations. If this small, fragile comet seemed to strain physics, it was because it was written by a different physics, a different beginning, a different history of ice dust light and collapse. The mystery endured not because physics failed, but because the cosmos had revealed a chapter humanity is only just beginning to learn how to read. As the mystery of 3I Atlas expanded into a landscape of chemistry, jets, memory and physics, stretched to its limits, one truth became increasingly apparent. No theory could stand without data, and no data would come without instruments capable of chasing an object both faint and fleeting. The scientific tools that had captured the anomaly were not monolithic. They were a global constellation of telescopes, detectors, surveys, spectrographs, spaceborne sentinels and computational engines, all reaching for a visitor dissolving slowly into interstellar night. In this pursuit, the effort to understand 3I Atlas became a quiet race against time. For interstellar objects, time is always short. They appear abruptly, move swiftly, and vanish into the cold before humanity can look twice. With 1I Oumuamua, the opportunity arrived too late. Researchers caught only its fading escape. With 2I Borisov, the window was better yet. Fragmentation stole the chance for prolonged study. So when 3I Atlas revealed its interstellar origin, early enough for observation, a global mobilization took shape, astronomers working across continents to gather every photon before the comet dimmed beyond reach. The first responders were the survey's Atlas Pan-STARRS, ZTF machines of vigilance scanning the heavens nightly with broad sensitive eyes. These surveys did not judge. They simply watched. And when 3I Atlas's rising brightness defied prediction, it was the surveys that kept the light curve alive, filling gaps between precision observations with steady, patient tracking. Their wide-field cameras captured the object's changing morphology, the widening coma, the shifting tail, the emergence of faint dust structures otherwise invisible to smaller instruments. From survey telescopes, attention moved to the major optical observatories. In Chile, the European Southern Observatory's 8.2-meter telescopes gathered deep spectral fingerprints from the faint light drifting across space. These spectra were the closest thing to touch chemical signatures, encoded in emission lines ratios and continuum shapes. They revealed not only the presence of certain volatiles, but the absence of others, the unusual dominance of fine dust, and the subtle thermal patterns hiding beneath the surface behavior. The Gemini telescopes, one in the north and one in the south, contributed high-resolution images that teased out the inner coma's structure. Adaptive optics sharpened these images, allowing astronomers to glimpse faint jets, slender plumes drifting off the nucleus like filaments of breath. These were the engines thought to be reshaping the object's brightness and motion. Yet even Gemini's power was limited. The nucleus itself remained unresolved, wrapped in a shroud of dust. Spectrographs on these observatories pushed further. Instruments like X-shooter and Fire passed the faintest whispers of light, revealing volatile compositions across ultraviolet, visible, and near-infrared ranges. Instruments hunted for specific molecules, hydroxyl, cyanogen, ammonia, and compared line intensities with models of sublimation. The mismatch between expected and observed ratios deepened the puzzle, hinting at exotic ices or delayed sublimation processes. Each dataset became a fragment of the larger mystery. Beyond Earth's atmosphere, spaceborne tools joined the chase. Though no mission was designed for interstellar comet interception, spacecraft like Hubble were flexible enough to be redirected, capturing images at resolutions unreachable from the ground. Hubble detected subtle asymmetries in the coma's structure patterns that suggested directional activity rather than uniform sublimation. Its ultraviolet sensitivity revealed faint gas emissions obscured from ground-based telescopes by Earth's atmosphere. These emissions hinted at volatile reservoirs out of equilibrium, reinforcing the idea that 3I Atlas was awakening not at perihelion, but in the cooling aftermath. Meanwhile, the Deep Space Network's radar arrays attempted to listen for reflections. The object was too faint and too distant for strong echoes, but the near silence was itself a data point. No metallic density, no large coherent surfaces, no monolithic fragment. Instead, the radar return suggested a porous body consistent with microfragmentation, structural weakness, and the slow unraveling described by the brightness curve. While telescopes gathered photons, computers gathered truth. Teams across the world ran numerical models simulating dust dynamics, internal heat flow, jet physics, rotational evolution, and structural collapse. These models required supercomputing power, thousands of cores working simultaneously to test possibilities. Thermal inertia models predicted how heat spread through layered interstellar ice. Fragmentation simulations explored how microcracks propagated under rotational stress. Dust dynamics codes traced the paths of particles through solar radiation pressure, reproducing the evolving curvature of the tail. None of these simulations provided a final answer. But together they narrowed the field of possibilities and revealed a picture with increasing resolution. 3I Atlas was not simply brightening, it was experiencing a complex sequence of internal chemical and structural transformations triggered by its encounter with sunlight. Radio observatories also played a role. The Atacama Large Millimeter to Sub-Millimeter Array ALMA, designed to detect faint molecular emissions in distant galaxies, trained itself on a small interstellar visitor. Though the signal from 3I Atlas was faint, ALMA's sensitivity captured emissions from gases difficult to observe in the optical range. Some molecules appeared in amounts inconsistent with expectations, hinting at unusual interior chemistry or deep sublimation sources. At the same time, solar observatories like SOHO and Stereo, though designed for solar monitoring, accidentally captured 3I Atlas in their wide-field coronagraphs. These images documented its behavior around perihelion, revealing subtle details of its brightness evolution that would later prove essential to understanding the delayed brightening. What SOHO saw was a comet that behaved almost normally during closest approach. Its anomaly emerged not in the heat of perihelion, but in the cooling escape afterward. Even amateur astronomers contributed. High-quality backyard telescopes equipped with CCD cameras tracked the comet nightly as professional observatories contended with scheduling constraints and weather. The precision and passion of this global community filled gaps in the light curve and captured dust structures that might have otherwise gone unnoticed. Some amateurs recorded faint morphological changes before any major observatory reported them, demonstrating how collaborative astronomy has become. Yet the most ambitious idea came too late to be realized in an attempt to design a rapid response mission, a probe capable of intercepting interstellar objects at short notice, similar to the conceptual Comet interceptor mission planned by ESA and JAXA. Such a mission, had it existed, could have performed close flybys, collected in situ spectra, mapped the nucleus, and perhaps even sampled dust. But 3I Atlas passed too early in history. Humanity was not yet ready. Still, the dream persisted. Every observation of 3I Atlas fed into future mission planning. Engineers began sketching designs for spacecraft capable of long-term loitering in stable points around the Sun, ready to launch at interstellar intruders within days. The comet drifting outward and dimming was already shaping the next generation of scientific tools, and as 3I Atlas receded, the last data points trickled in faint wavering precious. Observations continued as long as possible, until only the largest telescopes could detect it, until finally the signal dissolved into the background of stars. The pursuit ended not with closure, but with a quiet acceptance the object had revealed what it could. Its light curve, its dust, its jets, its structural decay, all recorded by an armada of instruments, would become the archive through which scientists would attempt to extract meaning for decades. 3I Atlas had arrived unannounced, brightened against reason, and departed unresolved, and the tools that chased it earthbound and orbital were left with only the echo of its passing, preserved in data streams that would continue to whisper their secrets long after the comet had vanished into infinite dark. As the interstellar visitor drifted farther into darkness, and the last photons from its fading coma reached Earth, astronomers began assembling the enormous archive of data collected during its brief sojourn. From spectral lines to dust models from tail morphology, to thermal simulations from Hubble's crystalline imagery, to the quiet measurements logged by backyard telescopes, every scrap of information was placed into the growing mosaic. And yet as the picture sharpened, the strangeness did not fade. Instead, the anomaly gained definition. For every question answered, two more rose in its place. What remained after months of analysis was not resolution, but a constellation of unresolved clues, each pointing toward deeper puzzles still hidden within the silence of interstellar space. The first unresolved anomaly lay within the light curve itself. The data made clear that 3I Atlas brightened after perihelion, but the exact shape of that brightening resisted modelling. No single physical process delayed sublimation, microfragmentation, thermal conduction or rotational modulation could reproduce the smooth rising curve with full fidelity. Instead, the light curve seemed to blend several mechanisms at once, each contributing in shifting proportions. Some nights matched the signature of fine dust dominating reflectivity. Others aligned more closely with sublimation-driven activity. Still others hinted at mass loss inconsistent with either. The curve refused to settle into a single story. The second lingering puzzle emerged from its gas production rates. While dust signatures overwhelmingly increased after perihelion, the gas lines did not always follow suit. Water production, expected to correlate strongly with overall activity, remained surprisingly stable or even decreased in some observations. This mismatch defied classical comet physics. If dust production rose dramatically, gas production should as well, unless the dust was not being lifted by gas at all. This contradiction strengthened theories of internal collapse or microfragmentation, yet even those models struggled to reconcile the full discrepancy. It was as though different layers of the nucleus were acting independently, each awakening according to its own buried rhythms. One of the most enigmatic clues lay in the spectral ratios involving carbon monoxide and cyanide. On some nights, faint enhancements in these species appeared only to vanish in subsequent observations. These fluctuations were not periodic, nor did they correlate with solar distance or tail morphology. If they were noise, their recurrence was suspicious. If they were real, they implied chemical reservoirs dispersed irregularly throughout the nucleus, tiny pockets venting momentarily before sealing or becoming obscured by dust. Such behavior suggested a nucleus riddled with microenvironments shaped by interstellar processes, not the smoother layers expected from solar system comets. The tail's geometry left its own imprint of ambiguity. Dust tracking models attempted to reconstruct when particular grains had been released, but results varied widely. Some grains appeared to originate from early post-perihelion activity. Others suggested release far later, even as the object dimmed. This indicated either continuous fragmentation or a shifting pattern of jet activity, yet the tail curvature did not match any consistent jet orientation. Some simulations suggested that jets turned on and off unpredictably, perhaps influenced by tumbling or evolving surface collapses. But tumbling itself remained unconfirmed. The nucleus was far too small and dust-shrouded for light curve periodicity to be measured reliably. Another unresolved clue came from the dust itself. Grain size distributions inferred from scattering patterns suggested an unusually high proportion of submicron particles, far finer than those typically produced by ordinary comets. Such fine grains reflect sunlight, efficiently explaining the steep brightness increase, yet their prevalence raised deeper questions. How could so many tiny grains form without violent fragmentation? Why were larger grains so comparatively scarce? Theories involving cosmic ray-weakened surfaces, frost layers, or fragile interstellar aggregates attempted to account for this, but none fully matched the observed scattering profiles. Even the coma's shape defied certainty. In images from large telescopes, faint asymmetric features appeared wisps, fans hints of structural variations that shifted slightly night to night. These might have been jets or microfragment clouds or illumination effects, but none persisted long enough to map with confidence. Their fleeting nature became yet another whisper in the archive, pointing perhaps toward a surface undergoing rapid, localized change, too subtle to capture in detail, too inconsistent to interpret definitively. The internal structure of 3I Atlas remained one of the great unanswered pages. Thermal models indicated delayed heating of subsurface layers, yet the depth and extent of this heating were uncertain. If heat penetrated deeply, it would imply a porous nucleus. If it penetrated shallowly, the delayed activity must come from near-surface layers. Neither scenario fully matched all observations. Similarly, the notion of internal voids or caverns carried explanatory power, but their distribution size and dynamics remained speculative. Without direct imaging of the nucleus, scientists were left to infer structure from behavior alone, a process as delicate as listening for architecture, by tracing the echo of falling dust. Chemical transformations also left their imprint on the puzzle. Cosmic ray-induced radicals, clathrate hydrates, exotic interstellar ices each offered insight, but none alone could produce the extended, smooth post-perihelion brightening observed. If multiple such processes overlapped, the behavior grew easier to understand but harder to pin down, for the exact interplay would require knowledge of composition that no remote observation could resolve. Rotational dynamics became yet another lingering question. The hypothesis that 3I Atlas tumbled was plausible but unproven. If true tumbling might explain shifting jet directions or irregular dust release. But without a clear periodicity in the light curve swamped by the intense dust activity rotation, remained a ghostly presence inferred but unseen. A nucleus rotating irregularly could produce many of the anomalies, yet without direct confirmation, the idea floated on the periphery of understanding. Perhaps the most profound unresolved clue lay in the object's interstellar provenance. Everything about 3I Atlas's behavior pointed toward an origin shaped by processes unrelated to the Sun. But without knowing the chemical and thermal history of its birth system, scientists could only speculate. Was it formed in a nitrogen-rich disk, a carbon-heavy nebula, a cold, ancient environment with long periods of freeze-thaw cycling? Each possibility held potential, but none could claim certainty. Even the rate of brightening remained ambiguous. Some models suggested it reflected increasing dust production. Others attributed it to decreasing grain size. Still others implied that the nucleus was slowly disintegrating. All three explanations were possible. Perhaps all three were true. In the end, what remained in the wake of 3I Atlas's departure was not confusion but wonder, a recognition that the universe had offered a puzzle too complex to be solved in a single passage. The anomalies persisted because they reflected layers of history buried within an object older than human species, shaped by a star humanity would never see. The unresolved pages in the archive were not failures. They were invitations, clues, awaiting the next interstellar visitor, the next fragile messenger carrying the chemistry of another world. 3I Atlas had left behind its questions. Humanity would turn them into tools, theories, missions yet unbuilt. The mystery would not fade because it lay not in the comet's behaviour alone, but in the deeper truth it revealed. We have only just begun to learn how to read objects forged in other stars. The deeper astronomers journeyed into the layered mysteries of 3i Atlas, the chemistry, the jets, the internal collapses, the unresolved anomalies, the more a quieter realization began to take shape beneath the technical discourse. It was not about a single object anymore, it was about the universe itself. About the foundations of planetary birth, the diversity of cosmic architectures, the profound truth that the Milky Way is not a single narrative, but a library of trillions, and 3i Atlas drifting outward, now shedding its final grains of dust into silence, had become not merely a scientific puzzle, but a symbol, one small shard of a forgotten world, reminding humanity that the universe writes far more stories than the solar system ever taught us to expect. Its behaviour, its rising luminosity, its delayed awakening, its chemical strangeness, forced scientists to widen their lens. They were no longer studying a comet, they were studying the artefacts of planetary formation across the galaxy. If interstellar visitors arrived with compositions unknown here, then the notion of typical planetary chemistry was an illusion. The solar system was one example, nothing more. A single stanza in a galaxy-long poem. Through this lens, 3i Atlas became a messenger. Not in the mystical sense, but in the deeply physical one, a courier of mineral boundaries, thermal histories and cosmic time. Every grain of dust carried structural memory. Every molecule radiating from its coma whispered of conditions that existed long before the sun ignited. The comet's behaviour was a physical echo of its origin, a star system whose light would never reach Earth, whose planets might have formed and dissolved eons before humans walked the planet. What lessons, then, did this tiny interstellar visitor offer? The first was diversity. The solar system's comets obey patterns baked into the chemistry of a disk that once circled a young orange-white star. But 3i Atlas defied those patterns, revealing that chemistry elsewhere could give rise to materials responding to starlight in unfamiliar ways. This meant that planetary systems across the galaxy might harbour ices we have never catalogued, minerals that never formed here, and compounds that only stabilise in the frigid outskirts of alien nebulae. A single anomalous light curve hinted at worlds where nitrogen might have flowed like rivers, or where methane clathrates were as common as quartz on Earth. The second lesson was fragility. For all its silence and distance, 3i Atlas revealed that interstellar travel is harsh. Objects cast into the void endure bombardment by cosmic rays, thermal contraction over unimaginable timescales, micrometeoroid strikes and chemical transformations induced by radiation. These processes fracture, weaken, erode. What entered the solar system was not the object as it once was, but the remnant of its remnant, the survivor of a million-year exile. The brightening may have been the slow disintegration of a body that had carried its memory too long. The third lesson concerned formation. If 3i Atlas contained exotic volatiles, fragile lattices, or deeply layered structures, then perhaps it came from a disk colder than ours, or from regions shaped by a different balance of radiation and chemistry. Planetary formation, once thought to follow familiar templates, might be far more creatively diverse. Some stars may form with disks rich in carbon, others in nitrogen, others in sulfur-bearing compounds. Some may spawn icy bodies containing supervolatiles that trigger their greatest activity not during warmth, but during cooling. The object's strange response to the sun, all that delayed awakening, hinted at conditions far outside the norms of the solar system. It was in a way a core sample from another world, revealing not its surface but its deep interior through behaviour alone. The fourth lesson extended beyond astrophysics into the philosophical, that humanity's models are prototypes carved from limited experience. Comet theory, born from centuries of observing solar system wanderers, is not wrong, but it is incomplete. There is no single universal template for how frozen bodies behave under starlight. The galaxy contains a spectrum of possibilities, each shaped by the environments in which they formed. 3i Atlas, with its stubborn refusal to dim, reminded scientists that their intuition is local and their understanding provincial. And then there was the final humbling lesson that the universe is not concerned with being understandable. It reveals itself only in fragments, in moments, in brief apparitions of interstellar ice that streak through our system before disappearing forever. 3i Atlas would not return. It would not offer a second chance at observation. The mystery it carried, the brightening that seemed to violate every rule, would remain partially unresolved. A chapter half read, a page torn from a book that continues onward through the dark, never to be held again. Yet in that fleeting glimpse, the comet left something invaluable perspective. The solar system, for all its beauty, is one world among hundreds of billions. And every interstellar visitor is a point of contact between our small island of order and the vast ocean beyond. They are the drifting fossils of distant dawns, the wanderers born from ancient disks around unknown suns. In their dust lie the signatures of metals forged in stars older than the sun. In their ices lie the whispers of cosmic rays, the molecular echoes of nebulae collapsing before Earth existed. 3i Atlas was one such fossil, a relic carrying the imperfections, fractures, and volatile memories of a world humanity will never see. Its behaviour, its refusal to fade, its quiet bloom of light, was not a failure of physics, but a reminder that the universe is built from stories far more varied than the ones humanity has had the chance to study. As it drifted farther from the sun, its glow thinning into the cold, 3i Atlas returned to the anonymity of interstellar night. But the questions it raised did not fade. They became a compass, a motivation, a promise that the next visitor and the one after that would bring pieces of the galaxy's vast diversity with them. The universe beneath one stone, this stone was larger, stranger, and older than anyone imagined. And the small fragile visitor named 3i Atlas had lifted one corner of the veil, inviting humanity to imagine the rest. As 3i Atlas slipped outward into the widening dark, its brightening curve beginning at last to shallow its dust, dispersing into a thin diffusion of particles too faint for even the largest telescopes to resolve, the long cosmic echo of its presence began to soften. What remained was a trail of questions, a scaffold of theories, a lattice of half-understood processes that refused closure. And yet beyond the technical and the structural, beyond the chemistry and the jets, there was a final layer to the mystery, one rooted not in data but in meaning. For every scientific puzzle the comet had left behind, it had also stirred something quieter, more human, more ancient. A sense of encounter, a sense of being brushed, however briefly, by something that came from far beyond the borders of the sun's familiar light. As researchers reflected on the strange luminosity of 3i Atlas, they began to see it not merely as an object misbehaving, but as a reminder of cosmic impermanence. Here was a body that had survived for eons, drifting alone between the stars. It had endured cold more absolute than anything earthborn materials could tolerate. It had carried within its fragile core the long, unbroken silence of interstellar space until a chance alignment of trajectories led it through the sun's domain, where the warmth of a foreign star awakened the quiet architecture it had carried for ages. What the comet revealed was not just the science of alien ices, but the vulnerability of all structures shaped by time. 3i Atlas approached the sun as one thing, and left it as another. It changed, it fractured, it brightened. It revealed its inner layers not through intention but through the simple inevitability of exposure. And in that quiet unravelling, it demonstrated a truth that applies not just to comets, but to worlds, to stars, to galaxies, to everything that moves through the cosmic unfolding, that nothing persists unchanged. Its brightening became in this light a kind of cosmic metaphor, an illumination, arising not from strength, but from transformation, from the collapse of old internal boundaries and the release of materials once hidden. What astronomers measured as an anomaly in the light curve could also be read as a universal pattern. When ancient objects encounter new conditions, they reveal parts of themselves that would otherwise remain forever unseen. In the philosophical quiet that followed the last observations, some scientists reflected that 3i Atlas had forced humanity to confront its assumptions about universality. The solar system is not a template for the cosmos. It is one island in a vast archipelago of star-born systems, each shaped by its own chemistry, its own radiation field, its own cycles of heat and shadow. To expect interstellar visitors to obey the rules written here is akin to expecting every language in the galaxy to follow the grammar of one village. The comet's behaviour, its delayed awakening, its internal instability, its quiet bloom of dust, was not just a scientific puzzle. It was an invitation to humility. Humanity's understanding of the universe has always been built upon limited samples, one star, one disk, one set of planets, one catalogue of ices. But now, for the first time in history, fragments from other star systems had begun to cross our path. They carried with them the architectures of worlds, never seen the chemistry of disks, never mapped the signatures of evolutionary paths that unfolded under suns that have long since burned out or moved on. What made 3i Atlas profound was not its brightness alone, nor the anomalies it carried, but the reminder that discovery is no longer confined to the solar system. The galaxy itself is beginning to speak through these wanderers. Each one is a messenger carrying the residue of its home, the imprint of its birth, the scars of its journey through interstellar night. As the object faded, slipping beyond the reach of telescopes, astronomers were left not with frustration, but with a sense of expansion. The mystery remained unresolved, but not in the way of failure. Rather, it remained unresolved because the universe had not finished its sentence. 3i Atlas was one letter, one syllable in a language humanity is only just beginning to learn. Future interstellar visitors will come, perhaps larger, perhaps closer, perhaps stranger still. With each one, humanity will refine its understanding of planetary formation, interstellar chemistry, and the evolutionary pressures that shape small bodies beyond the sun. One day a mission may intercept such a visitor directly sampling its materials, mapping its nucleus, walking its dust-laden surface, with instruments built to withstand alien processes. And when that day comes, the unresolved questions left by 3i Atlas will become stepping stones rather than uncertainties. For now, the comet drifts outward, carrying its final grains into a darkness it knows far better than we ever will. It leaves behind the faintest trace of light stored in hard drives, in archives, in the memory of those who watched its improbable ascent after perihelion. It leaves behind a reminder that the cosmos is not merely a place of stars and orbits, but a place of histories, each object a document, each trajectory, a sentence, each anomaly, an invitation to imagine what lies beyond the reach of familiar models. And perhaps that is the deepest meaning of 3i Atlas, that the universe remains vast not only in space but in possibility, that the stories carried by drifting fragments are older, stranger and more numerous than humanity has yet dared to believe, that within the faint brightening of one small visitor lies the promise that the universe is still writing, still sculpting, still revealing itself one interstellar wanderer at a time. It faded, yes, but in fading it gave shape to questions that will guide generations. In its retreating glow it left not an answer but a direction. And now, as the trail of 3i Atlas softens into the vastness, allow the mind to drift with it gently, slowly, as though following a small lantern carried into an endless night. The frantic brightness of discovery quiets. The telescopes fall still, the calculations dim. Across the long dark of interstellar space the comet continues on its dust spreading thinly, until even the memory of its shape dissolves. And in this dissolution lies a kind of peace, for so much of its passage through our Atlas stirred questions sharp enough to unsettle. But as its glow recedes, those sharp edges soften, the urgency fades, and the mystery becomes something gentler, an open horizon rather than a barrier. Its brightening once a paradox becomes a whisper. Its transformations, once a puzzle, become a reminder that change is simply the nature of all drifting things. The universe is quiet at this distance. Stars become a soft embroidery. Light becomes a slow, patient tide. Somewhere in that calm, the comet moves without haste, carrying with it the faint warmth it once borrowed, now fading into a cold older than memory. What it revealed remains behind the idea that even the smallest traveller from the unknown can reshape how we see the whole of existence. And so the story closes not with certainty but with gentleness. Let the last image be one of calm, a small ancient object drifting back into darkness, its final grains of dust scattering into the quiet. Let the questions it raised settle softly like snow across an empty field. The universe holds them. It will answer them in its own time, through its own wanderers, in its own quiet way. Sweet dreams.